Good morning, good afternoon, and good evening, everyone, depending on where you're joining us from today. Welcome to this webinar on HighFinesse wave meters and more, and thank you for taking the time to join us. Let me start by introducing ourselves. My name is Dr. Florian Karlewski. I'm the CEO of HighFinesse. Before taking on this role, I spent many years as head of research and development, working on laser metrology, wavelength measurement, and photonics applications. Dr. Arsen Dankov is our sales and service manager. With a PhD in nanoengineering and expertise in systems engineering and scientific instrumentation, he supports researchers worldwide in implementing advanced measurement solutions. Jazim Al-Nuwaida is also a sales and service manager. He holds a master's degree in laser and optical technologies and combines strong application knowledge with extensive hands-on experience in laser metrology and photonics. Together, we'll take you through today's webinar, and at the end, we'll all be available during the live Q&A session to answer your questions. Let's take a quick look at today's agenda. I'll start with a brief introduction of HighFinesse and then explain why precise wavelength measurement has become such an essential part of modern photonics. Then Dr. Arsen Dankov will introduce the HighFinesse technology and give you an overview of our product portfolio. Next, Jazim Al-Nuwaida will perform a live demonstration where you'll see our instruments characterizing and controlling a laser in real time. After that, I'll return to present several application examples from research and industry, followed by a brief look beyond wavelength meters and the broader HighFinesse portfolio, which will be again shown by Dr. Arsen Dankov. We'll conclude with a live Q&A session, so please feel free to submit your questions throughout the webinar. HighFinesse was founded in 2000 as a spin-off from the University of Tübingen. For more than 25 years, we have focused exclusively on high-precision wavelength measurement and laser metrology. Today, our instruments are used by leading research institutes, universities, and high-tech companies worldwide. Behind every HighFinesse instrument is a dedicated team of around 50 colleagues. Scientists, engineers, software developers, and application specialists work together to develop and support high-precision measurement solutions for customers around the world. HighFinesse serves customers worldwide through an international network of distributors and partners. Research, development, quality management, and final assembly are located in Tübingen in Germany, while our optics production is based in Serbia. Together with our partners, we provide local support across many countries. Many advanced laser applications require extremely stable and accurate wavelengths. Even very small wavelength drifts can influence experimental results, measurement accuracy, and system performance. Whether in atomic physics, quantum technologies, spectroscopy, or astronomy, reliable wavelength measurement is essential. This is exactly where HighFinesse instruments provide the required precision and stability. Let me start with a personal story. About 20 years ago, I was a student and I entered a quantum optics lab for the first time. My first task was to build a laser, an ECDL, an external cavity diode laser, from scratch. Just metal parts, a laser diode, some optics, and a grating. After a few hours of work, I finished the setup and I saw the first light coming out. That was already exciting. But the real challenge was still ahead of me. I needed to set the laser to a very specific wavelength. To find the right wavelength, I had only two tools: a rubidium spectroscopy cell and a night vision viewer, because the laser light was infrared and invisible to my eyes. The problem was, this laser has many degrees of freedom: grating angle, diode current, temperature, cavity length, and I had almost no feedback. I could only see if the light scattered on the rubidium atoms or not. That's it. No number, no wavelength value, just yes or no. Because of this, the whole process took me several days. Days just to get the laser to the right wavelength. With a HighFinesse wave meter, this exact same problem would have taken a few minutes, not days. And later, that's exactly what we did. We used the wave meter and suddenly this task became trivial. The next step was building a rubidium saturation spectroscopy setup and using that signal to stabilize, so to speak, to lock the laser wavelength. This gave us a real laser system that we could actually use for our quantum optics research. Again, this took a long time to build and optimize. But with a HighFinesse wave meter, this process is much faster and much simpler. What used to take weeks can now be done in hours. And today, you don't even need to build the laser yourself. There are excellent commercial lasers available. For example, from our partner TOPTICA, who make some of the best laser systems on the market. Here now comes the most important step. With spectroscopy, you can only stabilize your laser at specific wavelengths, exactly where the atoms have a resonance, nowhere else. But with a HighFinesse wave meter, you can stabilize your laser at virtually any wavelength you want. The only limitation is the tuning range of the laser itself. That changed everything. We no longer had to adapt our experiments to the available atomic transitions. Instead, we could choose the wavelength that was best for the experiment and lock the laser there with confidence. This was not simply a faster way of working. It opened up entirely new scientific possibilities. Experiments that were difficult or even impossible with traditional spectroscopy locking suddenly became feasible. Looking back, this is what makes wavemeter-based laser stabilization so powerful. It doesn't just save time, it gives researchers the freedom to work at the wavelengths their science requires, rather than the wavelengths the reference dictates. So let me summarize this story. With HighFinesse wavemeter technology, what used to take days or even weeks can now often be done in minutes or hours. That means less time spent aligning and troubleshooting and more time focused on the actual science. But for me, that's only half of the story. The real value is that precise wavelength measurement gives researchers confidence. Confidence that the laser is doing exactly what they think it is doing. And when you have that confidence, you dare to explore new ideas, new wavelengths, and new experiments that would otherwise be too difficult or too risky. That is why precise wavelength measurement matters. It doesn't just make research faster, it enables better science. So here I like to hand over to Dr. Arsen Dankhoff, who will explain to you how our technology works.
Thank you, Florian. Before looking at our products, it is helpful to understand how they actually work. Our wavelength meters are based on the Fizeau interferometer principle. At the core of the success of our wavelength meter lies the Fizeau interferometry. When light enters the wavelength meter through a fiber, it is guided by several mirrors and passes through our proprietary Fizeau interferometer system. Thus, an optical interference pattern is generated and is focused by a cylindrical lens onto the instrument detector. Complex software algorithms then evaluate the pattern and determine the absolute wavelength of the laser. Once you have such a powerful measurement tool, you can build much more than a wave meter. The absence of moving parts makes the system robust, fast, and highly reliable. The same technology supports continuous wave and pulse lasers over a wide spectral range. It can monitor multiple lasers simultaneously, integrate into automated laboratory systems through our API, and synchronize measurements using external triggering. In other words, the Fizeau technology is not only the heart of wavelength meters, it enables an entire ecosystem of laser characterization and control solutions. And that's exactly what we'll continue exploring throughout today's webinar. With that understanding of the technology, you will now see how it's implemented across the HighFinesse product portfolio. Before we continue to the product portfolio, I'd like to put our technology into perspective. There are several ways to measure laser wavelength, and each technology has its own strengths. Let's first look at the accuracy. On the one end of the spectrum, we have spectrometers and wavelength meters based on the microson interferometer. These instruments have a fairly limited accuracy. At the other end of the spectrum, frequency comms and ultra-low expansion cavity systems provide extremely high accuracy. However, as we can also see, they're very expensive and complex. Fizeau-based wavelength meters, like those from HighFinesse, occupy what we believe is the sweet spot. They provide outstanding absolute accuracy while remaining fast, robust, and easy to use in everyday laboratory environments. In other words, they deliver the performance needed for demanding research without the cost and complexity of the most advanced reference systems. That combination of accuracy, usability, and cost effectiveness is what has made Fizeau technology the preferred choice for thousands of laboratories worldwide. Now that we have looked at the technology behind our wavelength meters, let's look at how we've translated that technology into a complete portfolio of solutions. Most people know HighFinesse for our wavelength meters, and they remain the core of our product family. But over the years, we have expanded this platform with complementary solutions, including optical spectrum analyzers, line width analyzers, calibration sources, and multi-channel fiber switches. Together, these products support researchers throughout the entire process of laser characterization, stabilization, and measurement. For precision laser diagnostics and control, our core portfolio consists of wavelength meters, laser spectrum analyzers, line width analyzers, calibration sources, and multi-channel fiber switches. Each product family addresses a different measurement challenge, but they all share the same philosophy: delivering highly accurate, reliable measurement data for demanding photonics applications. Today, we'll focus primarily on the wavelength meter, followed by our multi-channel switches, since these are the products that you will see in the live demonstration later in this webinar. Let's start with our flagship products, the WS8 series wavelength meters. The WS8 series is designed for researchers and engineers who need the highest possible measurement accuracy. Our WS8-2 wave meter is able to reach an absolute accuracy of plus minus 2 megahertz. This makes the WS8-2 the most accurate commercially available wavelength meter on the market today. Such accuracy is essential for applications like quantum technology, atomic physics, precision spectroscopy, and optical metrology, where even very small wavelength deviations can affect the experiments. On the next slide, I'll show you some of the other key features that make the WS series so powerful. Of course, accuracy alone is not enough. A wavelength meter also has to fit into the way researchers work every day. This is why the WS series combines high accuracy and high speed with excellent stability and easy integration into laboratory environments. Depending on the model, the instruments support both continuous wave and pulsed lasers over a wide wavelength range. Additionally, we offer very fast wavelength meters in our WF series that measure wavelength so fast that the measurement resembles the feeling of an oscilloscope. This allows users to observe wavelength changes in real time, which is particularly useful during laser alignment and optimization. The instruments can also be integrated into automated setups through our software interface, making them suitable for both laboratory research and industrial applications. To supplement and enhance the functionality of our wavelength meters, we also offer various different options, such as external trigger for synchronization of the measurements with external events, PID laser control for precise locking of the laser, multi-channel switches and multi-channel laser controllers, which are essentially a combination of the previously mentioned two solutions. And we also offer line width estimation options and the option to include additional instrumentation for the measurement of the laser spectrum itself. Last but not least, we offer external calibration sources for our wavelength meters. Aside from our tabletop wavelength meters, we also offer our WR series. It uses the exactly same high finesse measurement technology and delivers the same accuracy and reliability. The difference is the form factor. The WR series wavelength meters are built in a 3-height unit 19-inch rack for seamless system integration. Many research laboratories work with more than one laser. Measuring each laser with a separate wavelength meter is often unnecessary and can significantly increase both cost and complexity. Our multi-channel fiber switches provide an elegant solution to this problem. They allow multiple laser sources to be connected to a single high-finesse wavelength meter with fully automated switching between the channels. This makes it easy to monitor and characterize several lasers using one measurement system while maintaining the same high accuracy and reliability. Together with our wavelength meters, the switches form a flexible and scalable solution that can easily adapt as laboratory requirements grow. Our fiber optical switch portfolio is available in a range of configuration to meet different application requirements. Depending on your setup, you can choose between 2, 4, or 8 channels, allowing you to monitor multiple lasers with a single high-finesse wavelength meter. We also offer different types of switches, including single-mode, multi-mode, and photonic crystal switches, to support a wide variety of laser systems and wavelength ranges. This flexibility allows researchers to configure a system that matches their experiments today, while keeping the possibility to expand as their setup grows. Together with our wavelength meters, the fiber switches provide a scalable and efficient solution for automated multi-laser measurements. Now that you have seen the key products we'll be using, it is time to see them in action. I'd like to hand over to my colleague Jasim for the live demonstration.
Thank you, Hassan. Now we will proceed to the live demonstration section of this video. In this live demonstration, we're going to show you the measurement using our wavelength meters and what you can expect once you acquire our instruments and want to set them up and install the software and how the software will look like. So just to make you feel familiar with our instruments. I have the setup ready right beside me. I have an SLR 780 laser and the photonic crystal switch and a WS8 II. And we have already prepared a video to show you in close-up how the setup looks like. And for this, we're going to play the video that will start in a moment.
Hello, my name is Jasim from HighFinesse Sales and Service Team, and in this video I'm going to show you how easy it is for you to set up your wavelength meter and start your measurement, and then we will dive into the software and how you could use it and the different units and options and different features that you can benefit from. So let's go to the setup. Here we have the SLR 780 laser. This is the calibration source that can be used with the wavelength meter. It uses a rubidium cell and it's locked to a well-known atomic transition. As a rule of thumb, the calibration source that you use with the wavelength meter should be at least 5 times more accurate than the wavelength meter specified measurement accuracy. And here you can see the frequency and the wavelength once the laser is locked, and the output from the laser is then going through this single mode fiber, which has an FC APC connection, and this goes into the input of our photonic crystal switch. This has a 4 channels input, and the output goes through this fiber and into the wavelength meter. Now, the photonic crystal switch, as my colleague Asen have already said, this has a wide transmission range that goes from 370 to 2000 nanometers, so you have a broad transmission range, and the unique feature is that you are always guaranteed to have a single mode output from the switch, which will then be used as an input to the wavelength meter. Here you can see the the wavelength meter input port, and this right here is the WS8 wavelength meter. This is the latest version for the WS8. If you have already owned some of our wavelength meter, you will immediately notice that this is a different casing. This is the metallic casing, which adds to the robustness that you already have by having non-movable parts inside. So unlike other wavelength meter where you have, for example, a movable mirror or so, here you have the robustness from the Fizeau interferometer inside that is always stable and non-movable. In addition to this, you have the new casing, and then you have the connection to the computer. So let's maybe go to the connection. So your switch is connected to the wavelength meter via a LEMO cable, and this is simply connected to wavelength meter from the TTL port on the backside, and your wavelength meter is connected via USB to the computer. And that's mostly it. This is most of the setup that you will need in order to start your measurement. After that, all you have to do is install the software on your computer and start it. In the next section, we will dive deeper into the wavelength meter software and the different measurement option that you can expect while using it.
Okay, that was me in the past. Now this is me in the present. I'm going to share my screen and show you the software. Okay. So as soon as you install the software on your computer and open the graphical user interface, so this is what you see, and immediately you see there's 2 big windows, one called interferometers, the other is interferometer. Basically, these are the imaged interferograms on the CCD from the interferometers that are used, and the combination of both of them, this is what at the end gives you this precise and accurate measurements. And you could see, for example, that there are several interferometers, not one, and this is usually shown by this small sections here. So here you can see there are 4 interferometers, and here we have one long one. And in the horizontal axis, this is the pixel numbers of the CCD array, and in the vertical axis, this is the intensity in arbitrary units. And you will be able to see when these interferogram peaks are high or low, this will give you an idea if your measurement is about to be overexposed or underexposed. So on the left-hand side, you will see the different options that you can choose from in the software. The first one is the result unit. So in the scientific field or in the labs, depending on your application, you might have a different preference for what you would like to be displayed, and you have the freedom to choose between the frequency or the wavelength in vacuum or the wavelength in air or the wave number, for example. And this can be easily changed in this part of the graphical user interface. Underneath it, as we have briefly mentioned, you could use the wavelength meter to measure continuous or pulsed lasers. And with the pulsed lasers, we have certain pixel in the CCD array that will wait for a certain intensity value, and on the rising edge of that value, the measurement will be enabled and you will be able to see your measurement. If you have ordered the trigger option in the beginning, because this is something that has to be implemented inside the wavelength meter, you will find two modes for the trigger. And the goal here is you want to synchronize your measurement with an external trigger, and you have two modes. The main difference between the two modes is in the mode 1, once you send a TTL signal, this is where your measurement will start. And when you send the other signal, this is where your measurement stops and the next measurement starts. With the mode 2 is different. When you send a signal, yes, the measurement starts, but it will choose the exposure time that you have already set in the software. And then within the precision section, you have fine and you have wide. And by the wide, you can get it from, you can see already in the displayed result. This is the rough measurements of the frequency over the wavelength. With the fine, you are really benefiting from both the windows here to provide you with the fine and precise measurement. Now, as I mentioned, I have a photonic crystal switch connected, and you have the option to enable this. And this can be enabled in the switch mode. And when you enable the switch mode, you will see where your laser is connected to. And currently, I am connected it in the 4th channel. And this is what you could see. So I have 4 measurements, 4 channels. On the 3 channels, nothing is connected, while on the 4th channel, I have my laser connected. And you have the options to show, but nothing will be showed now because there is nothing connected, but you could already see the lines that for each of these channels will be displayed in a separate, different color. Since we are only using 1 channel, we can switch off the switch mode. And you have underneath it the auto calibration option. Now, with the auto calibration option, from the name itself, you can imagine, okay, you want to run your experiment over the weekend or over several days, and you don't want to calibrate your wavelength meter every, say, 1 hour or every few minutes. All you have to do is enable the auto calibration option, and then the wavelength meter itself will calibrate depending on the channel you select for calibration. Now you have different display option you can choose from. So this is just if you would like to not see the interferograms at all, you could also remove it. Some customers prefer to do this because it may increase or make your measurement a little bit faster, meaning faster measurement rate. So these are different, depending on your preference, you can switch those on or off. Now, on the bottom side here, this is the displayed result, and you can switch between the different channels simply by clicking the channel you would like to use. Of course, the other channels are underexposed because nothing is connected, but the 4th channel that we are using, this is the one that is currently active. On the right-hand side, this is the exposure value. Currently, I set it to automatic exposure. Now, you could also remove the automatic and you can change the exposure as you want, but I keep it for convenience to automatic. With automatic, the software itself increases the exposure until we reach a valid, or until a valid measurement can already be taken. So it's less work for you and more work for the software to do. You can also decide how on which intervals you would like to do your measurement. You can set it here in the interval box, and here it is set to 500 milliseconds, but you could also turn it off if you want. You remember a minute or so ago, I informed you about the auto calibration. Well, you also can decide how often you would like to calibrate. And since this is a WSA2 wavelength meter, we do recommend that you calibrate it more often, because the idea is the more precise and the more accurate the wavelength meter is, the more likely you will need to calibrate it to reach that unmatched measurement accuracy. You also have the possibility to do average on the to do averaging on the results that you acquire. Now, if you would like to record your measurement or to save the interferograms that you have here, you have a few options. Now, for the recording, you can, for example, go to Operation, Start, Recording, and when you do that, you can then decide where you want to save it and simply click Save. Here it's in German, Speichern. You also have the chance to select what you would like to use. You can select binary if you would like to repeat, so if you would like to replay the recording on the software itself, or if you would like to export it and use it externally, please select the LTX option. That will be better for you. For the calibration, this simply can be done in Operations, Calibrations, Wavelength Calibration. And here you have several options. You can choose a HiNe or another laser. In our case, we are actually using another laser. As I said, this is the rubidium-based calibration source that we have. And yeah, this is what you can do, and simply press OK to calibrate your wavelength meter. Now, in addition to this, you also have the long-term graph. And in the long-term graph, this is where you would like to have a look at your measurement over, say, several days, or you would like to monitor your laser and see if it's drifting or not. And you could do that over a long period of time. And you could also see, for example, the standard deviation of your measurement. And also, as I have already shown in the previous graphical user interface, you could also select which unit you would like to use for these long-term measurement. You also have the chance to also save it. So you can click File, Save, and then simply save it as an LTA file, which can be also loaded later on if you would like to do more post-analysis. You could, in addition to this, you have different charts that you can select from. So you would like to see, for example, to see the temperature and how it changes with your laser measurements. And in addition to this, you could also add the pressure or the power, or you would like to add another signal or channel that you would like to view over the long term. This all is possible with the long-term graph. And I just explained a lot of things. Probably not all of our customers use all of these options, but this really depends on your application and what you would prefer to have. So this is mostly it for the live demonstration. Now we will head to the next section with Dr. Florian Kalewski.
Thank you, Jesse. So now let's move from technology to application. I want to show you where our core feature, highly accurate absolute wavelength measurement, actually makes a difference in the real world. The applications we are about to show you comes from one single outstanding feature: highly accurate absolute wavelength measurement. With this, you can do two things. You can monitor a laser's wavelength or just observe it without touching anything, or you can use that measurement as feedback to actively control and stabilize a laser. From this one capability, applications follow naturally. Obvious ones are spectroscopy, where a wavemeter adds an absolute wavelength axis to your measurement, or working with a frequency comb or an ultra-stable cavity, where the wavemeter helps you to find the correct mode, making sure your system is locked to the right absolute frequency, not just any nearby resonance. Now let's look at 4 concrete examples. The first application is laser guide star astronomy. Large telescopes shoot a laser into the upper atmosphere to create an artificial star. This is used to measure and correct atmospheric distortions in real time, a technique called adaptive optics, enable much sharper images of real astronomical objects. For this to work, the laser wavelength must stay precisely stabilized, even though the whole system runs outdoors under harsh conditions, temperature changes, vibrations, and remote unattended operation for long periods of time. HighFinesse wavemeters stabilize these lasers under exactly these demanding real-world conditions. Proof that our technology performs not only in a clean lab, but out in the field. The second application is LiDAR, light detection and ranging. Unlike other examples in this talk, LiDAR often uses pulsed lasers rather than continuous wave lasers. HighFinesse wavemeters can measure both. One example is the German Aerospace Center, DLR, which uses LiDAR systems for atmospheric research. By sending laser pulses into the atmosphere and analyzing the returned light, researchers can measure things like wind speed, aerosol distribution, and greenhouse gas concentrations at different altitudes. For these measurements to be scientifically meaningful, the exact wavelengths of the pulsed lasers must be known with high precision, and that's exactly where our wavemeter comes in. Quantum technology is one of the fastest growing application areas for HighFinesse. Modern quantum computers rely on multiple highly stable lasers for cooling, trapping, manipulating, and reading out atoms or ions. Precise wavelength measurement and laser stabilization are therefore essential. HighFinesse is involved in several leading quantum initiatives. For example, Munich QC Atoms is part of the Munich Quantum Valley and develops neutral atom quantum computers for applications in quantum chemistry and material science. RIMAX-1 is developing scalable quantum computing systems aimed at solving real-world computational problems. And QRX focuses on secure quantum communication by developing quantum repeaters that enable long-distance quantum networks beyond the limits of today's fiber optic communication. These projects illustrate how HighFinesse instruments support cutting-edge quantum research by providing the precision and stability required for next-generation quantum technologies. The fourth application is optical atomic clocks, and specifically the OptiClock project. This started as a research consortium led by PTB, the German National Metrology Institute, together with TOPTICA. The goal was to build a compact, transportable optical atomic clock, far more precise than traditional atomic clocks based on microwave transitions. Optical clocks have applications in precise timekeeping, navigation, and fundamental physics research. What's especially nice about this example is that OptiClock didn't stay a research project. It has since been commercialized and is now available as an actual product. From a demanding research requirement to a proven solution to a real-world commercial product. with HighFinesse wave meters playing a key role throughout. Here you see one of the OptiClock consortium meetings hosted by HighFinesse. Custom solutions have always been part of HighFinesse. Every application is different, so standard products are not always enough. Over the years, we have developed customer-specific solutions ranging from specialized interferometers to custom electronics and software. We work with leading research institutes such as NASA, ESA, DLR, MIT, and ETH Zurich, as well as industrial partners like Canon and many other high-tech and photonics companies. Whatever the application, our goal is always the same: understand the challenge and provide the right measurement solution. China is another excellent example of the strong reputation HighFinesse has built within the scientific community. Our wavelength meters are used by many of China's leading universities, as you can see here in this list. This broad adoption demonstrates the trust researchers place in the accuracy, stability, and reliability of our instruments for demanding scientific applications. So, for the last part, beyond wavelength meters, I like again to hand over to Asen.
Thank you, Florian. So far, we've focused on our wavelength meters and the applications they enable. As we have showed a quick overview of our portfolio in the beginning of the webinar, HighFinesse offers much more than wavelength measurement alone. Building on the same expertise in precision optics, interferometry, and laser metrology, we have developed a broader portfolio of instruments that help researchers characterize, calibrate, and stabilize their laser systems. Let's take a look at these products, starting with our calibration sources. Every wave meter needs to be calibrated regularly to maintain its accuracy. How often depends on the accuracy level. Entry-level wave meters only need calibration about once per month, and that can be done using their built-in calibration source. But our most precise instrument need calibration much more frequently, sometimes every few minutes, and this requires an external, highly accurate reference laser, usually stabilized to an atomic or molecular transition. To make it easier for our customers, we offer these reference sources directly. Some, like the SLR 780, were fully developed in-house at HighFinesse. Others we source externally, but we verify their accuracy ourselves before making them available, so customers can trust the whole calibration chain from start to finish. Our calibration sources make precise wavelength wavelength calibration simple. They are available in multiple wavelengths and accuracy classes, down to 0.5 MHz absolute accuracy. They are plug and play, require hardly any maintenance, and eliminate the need to build and maintain a complex spectroscopy reference setup. The result is fast, reliable calibration throughout the lifetime of the wave meter. Another instrument in the HighFinesse portfolio is our Laser Spectrum Analyzer, or LSA. Unlike a wave meter, which measures the central wavelength, the LSA shows the complete optical spectrum of the laser. That means you can identify multiple laser lines, side modes, and other spectral features that remain invisible in the wavelength measurement alone. The LSA combines high spectral resolution with fast acquisition and supports both continuous wave and pulsed lasers. Its grating system contains no moving parts, making it exceptionally robust and virtually maintenance-free. This also means that unlike rotating grating spectrometers, the LSA is lightning fast, allowing you to capture fast laser spectrum dynamics. The result is reliable, high-quality laser spectral analysis for both research laboratories and industrial applications. Finally, knowing a laser's wavelength is only part of the story. The next question is, how stable is that wavelength over time? That is exactly what the line width analyzer measures. It reveals frequency noise and laser line width, helping researchers characterize and optimize the stability of their laser systems. The line width analyzer doesn't just measure the laser line width. It also reveals the complete frequency noise density spectrum, showing how your laser behaves over time. That helps identify noise sources, optimize stability, and verify performance in real time. It's an essential tool for ultra-stable lasers in quantum technology, precision spectroscopy, and optical clocks. HighFinesse is more than a wave meter. We have built an ecosystem of products around laser measurement and control, from spectrometers and line width analyzers to calibration sources and multi-channel switches. Together with our custom solutions, we can support applications ranging from individual research labs to complex industrial systems. Everything is designed with one goal in mind: helping our customers fully understand and control their lasers. Before moving to the Q&A session, we would like to share one additional resource with you. We will place a quick share link in the chat. This link provides easy access to technical information about our products. From the quick share page, you can select the product category you are interested in and access the corresponding brochures, technical specifications, and QR codes for additional product information. Feel free to share this link and save it and share it with anyone who might be interested after the webinar. We hope this resource will be helpful as a reference after today's presentation. And now we would be happy to answer your questions.
So the questions are in the chat. Jasim, will you start with the first one to answer?
Yes. So let me read the question. The question says, what is the internal absolute reference standard in a wavelength meter? HighFinesse offers several wavelength meters with different levels of accuracy. Do they differ in their internal reference sources? So I would say that it's likely a question about the internal calibration source that some of our wavelength meters have, and when do you need another reference to calibrate your wavelength meter? So in our brochure or in our spec sheet, you will see that we have various products. Some of them, they differ mainly in the absolute accuracy. From the WS5 to the WS760 wavelength meter, except for the IR, you would have an internal calibration source that you could use. This is going to be, you can easily select it when you go to the operation calibration, and then you can select the neon lamp option in the software, and then you can calibrate. Now, when you go to the more accurate wavelength meters, this is when you will need a more accurate calibration source to use. And the rule of thumb is always, as we said, 5 times more accurate than the wavelength meter measurement accuracy. Now, from there are a few options that you can choose from. We do offer some options like the LFR1532 or the SLR780 that we have seen in the live session. And you could use some of these calibration sources. Okay. So next question is, what does the accuracy of the line width estimation refers to? Measurement resolution. No, these are two different things. So the line width estimation, this is a feature that you can order when you purchase or after you purchase the wavelength meter, and this is available for all of the wavelength meter except for the WS8-2s and the WS8-10 wavelength meters. With the line width estimation option, you have a specified accuracy for this option. For each of these models, for example, the WS6200 has a line width estimation accuracy of 400 megahertz, but you should always remember that the line width estimation accuracy is not better than 20% of the line width of the laser you're measuring. So if the laser is 2 gigahertz, then the estimation accuracy will not be better than 400 megahertz. Now, measurement resolution is something different. Measurement resolution is the we specify it as the standard deviation of the wavelength noise of your measurement. And you could imagine these are the small fluctuations that you see in the wavelength meter. And the idea is your the wavelength meter should have a very good low noise for you to see the next measurement. And if your measurement is within that noise, you will not be able to see the your measurement, or you would not be able to characterize it. And with the WSA2, for example, the resolution is 100 kilohertz, and this is very high and very useful if you would like to characterize your laser. Now, for the next two questions, I think Hassan, you can take over from there.
Can you mute, just?
Yes.
So question number 3 is why Fizeau interference-based measurement of HighFinesse can measure such a large range of wavelengths with such a high accuracy. So without revealing any company secrets, I would say to a large degree, this is based on the fact that we use multiple interferometers inside our instruments. We also characterize our instruments at multiple wavelengths with stabilized lasers. The range of wavelengths that can be measured by each wavelength meter range is, of course, dependent on the detectors inside the instrument itself to some degree. And therefore, we have mostly two different ranges. One is the standard range from 330 to 1180, and the UV ranges. And then we have in the IR range, we use different detectors. So this is what basically determines the wavelength ranges of the instruments. Fourth question is, how can switching speed and measurement efficiency be optimized when using a wavelength meter in conjunction with an optical switch? So the switching speed itself, it takes 12 milliseconds to switch between channels. So this is fixed, but it can be also slightly modified in the software. The question is how to optimize measurement efficiency. I'm not really sure what is meant by measurement efficiency. If it is referring to the stabilization of multiple lasers, when you have a switch with PID regulation, of course, the PID regulation bandwidth will drop the more channels you enable. So one simple way would be to disable any channel that is unused. That will increase the regulation bandwidth of the wave meter. Fifth question, Is HighFinesse able to measure at 193 nanometers or even EUV? Our UV2 range is specified until 192 nanometers. Below 192 nanometers, at the moment, we have no standard solution readily available. But it would be interesting for us to hear any potential use cases below 192. One point which is important to consider is, of course, that our wavelength meters have a certain FSR of their interferometers. And as a rule of thumb, we say that if the laser is broader than about 1/3, let's say, of the FSR, as a rule of thumb, it cannot be measured reliably due to overlapping effects. Therefore, the respective source has to comply to some degree with this principle. And some of these sources are fairly broad and unstable to be measured with a wavelength meter below this wavelength. Okay, can I obtain the line width of the input laser from the wavelength meter? So the answer is you can if you have the line width estimation option for your wavelength meter. The line width estimation option is available from the WS5 throughout the WS6 series and the WS7 series. It's not available by default for the WS8 series, which are the most accurate ones. The limitations of the line width options were mentioned by my colleague Jasim when answering one of the previous questions. Okay, Jasim, do you want to take some?
Okay, so the next question. The wavelength meter can display readings in the kilohertz range, but its absolute accuracy is 2 megahertz. Can it still be used to measure the frequency stability of a laser with fluctuations in the kilohertz range? So you are able, yes, to go beyond that because we also have the measurement resolution specified for the wavelength meter. And in addition to this, if you are using, for example, the API, and this is something very useful if you would like to use, for example, Python or LabVIEW, you can decide how many digits you can display and you can take a closer look at the measurement resolution and these fine fluctuations or noise that you see. The next question, when will the wavelength meter measuring 9.4 micrometers be released again? I think this is a question maybe Florian, you might be a better person to answer this.
Yeah, but I don't have a really good answer on that. This whole product series had to be stopped because of the geopolitical situation we are all in since some years. And until now, for certain parts, we don't have a sourcing alternative. So in general, if we find it, we would be happy to have them again. But at the moment, it's not foreseeable when this will take place. So the answer is at the moment, we don't know. I think I can also continue with question number 9. Can your LWA measure RIN? We have different series and types, and there is one type, which is the LWA 1K1550. So it's our highest precision instrument, and it's working in the telecom range. That one can measure the RIN. The rest, the others don't have that feature. Question number 10. Are there any examples of applications using LWA? So I can think of two examples. One which is regularly happen for us is that laser manufacturer or laser module manufacturer or whatever use the LWA for their R&D to develop laser sources, or in the quality part of the production to make sure the produced lasers are within the quality requirements. And another application which is which I have in my mind is in these quantum technology labs or startups or whatever. They also often have high demand on the laser frequency noise, and they want to see it, they want to measure it out of the measurement loop, out of the locking loop. And there the LWA can be a very, very helpful tool to see how the laser is performing, to see how the locking systems are performing, and to be sure that not the laser noise is preventing the quantum system to work as it should work. So that are two examples I would have here in my mind. Should I continue, or does someone else want to take over again?
I can take over again.
Yep.
So the next question is, how robust is the wavelength meter's performance? Can it work under around 50-degree temperatures in the summer? I would strongly discourage using it above 28 degrees C, as specified in the instrument manual. Above this temperature, roughly, there might be changes to some of the materials inside the instrument. This is not to say that the instrument will be destroyed immediately. However, it is strongly discouraged. And I should remind that the instrument is meant for indoor use in a roughly laboratory type of environment without large temperature and pressure fluctuations, which will affect the accuracy of the measurement. While it does have a temperature and a pressure sensor inside, the corrections are only accurate up to the first order, and higher order fluctuations cannot be fully compensated for. So it does pay off to try to ensure a normal operating condition for the wavelength meter. If you want to use your wavelength meter under more extreme conditions, I would recommend to first contact us, and then we can look at what type of solution we can provide for these more non-standard conditions that you might have. So the next question, I'm not really sure. Florian, can you answer it?
I'm not sure if it's about the line width estimation option of the wavelength meter. In that case, the whole estimation works with the broadening of the interferogram. We can see this is what the algorithm is based on, and we make some assumptions how the laser is, how the shape of the laser is. And if you look at the numbers that Jasim has been telling you, you can see it's anyway not that accurate that we make a difference between Gaussian or Lorentzian line width. So for the line width estimation option, it doesn't play a role. On the other hand, on the line width analyzers, yes, you can see the spectrum in the end of the laser, and you can, for example, export the data and fit whatever you want to fit. So you could use a Gaussian or Lorentzian distribution, and so that's taken there into account. That's the difference between the two instruments. Question number 13. Does HighFinesse wavelength meter have an overall solution specifically designed for optical module testing? So on the one hand, no. So we don't have a telecom solution like test and measurement solution that is ready to use. On the other hand, yes, we know that our instruments are used in R&D labs and in production for those telecom optical modules. I think what has to be mentioned here is that all the wavelength meter need a single mode laser. So if you have an optical module with a lot of lines, it will not be possible to measure. But individual telecom lasers, yes, because of the high speed, the robustness, the accuracy, there are a lot of reasons to use it in that context. Okay, question number 14. If a multi-peak pulse laser can be measured, here the simple answer is no. We need single mode for the lasers, and there can be cases where it's possible because the lines are so close that the wave meter just sees it as a single peak pulse. But in general, if you have the pulses far apart from each other, it will just show you bad signal or multi-mode signal, so it will not be possible. HighFinesse right now is 0% of US component. I think for that specific question, please contact our distributor, TCN. They can then connect here with our experts for all these customs stories. I think the answers here are not simple enough for a webinar. Okay, 16. What are applications of HighFinesse in daily life? Oh, that's strongly depending on your daily life. So if you are a scientist in a lab, probably it's more important as if you work in another field of science. But I think HighFinesse instruments, wavelength meters are used in science and R&D, and then products and other technologies are developed who might be influencing your daily life. For the direct application, I don't have an idea or example. What about my colleagues? Do they see a connection?
Well, if you have your PhD, you're doing PhD or master's, it can make your life much easier, just like it happened with the Florian when he was a student. I would say that's a very, that's a daily, that's a life-changing instrument,
Yeah,
I would say.
yeah, and probably in our audience there are a lot of people from that direction, but I think for the 99% of the people it's not the case. What are the requirements for measuring pulse lasers? Arsen, do you want to answer that question?
Yes. So to some degree, I have measured. We have mentioned already two of the requirements. The pulse needs to be roughly single mode, and we have to obey the conditions of the FSRs to not have too wide of a pulse. If you have wider pulses, let's say below or around a nanometer in width, this can be measured with our LSA. This instrument is perfectly suitable for measuring broader sources that cannot be measured by the wavelength meter. They will also give a reading of the wavelength, of course not as precise as the wavelength meter, but still very good. And they will give you the optical spectrum, so you will be able to see how the optical spectrum of that pulse looks like. And the next one is, can a wavelength meter achieve high precision measurements that are immune to environmental influences? Is periodic calibration required? So complete immunity to environmental influences is a thing that is very hard to achieve, but periodic calibration is one of the things that corrects for changes in the environment. In fact, we recommend that if the temperature changes by 1 degree or more, to recalibrate the wavelength meter. Okay.
So we are at the end. of our webinar today. Thank you very much for joining us here. And we hope you enjoyed the webinar and found it informative. We look forward to hearing about your questions, your applications, and your measurement challenges. Thank you. Have a great day and goodbye.